This is one of the definitions for the Riemann zeta function, the one that we see the most. It's this infinite series where your input is the exponent and then you're adding all these terms with the bases increasing. It's just a way to say 1 plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s. Just pick a value for s, right? And then this will give you a number if it's in the right domain. And although this isn't the most complete definition, there are more definitions, the analytic continuation, to different regions of the complex plane. This works for any number whose real part is above 1. This converges for any number whose real part is above 1. So what are we going to do with it? You can actually factor this, and it's like a prime number sieve. And I'll just go ahead and start with it. So first, we can go ahead and multiply this by the second term right here, 1 over 2 to the s. Okay, so basically what this does is it just doubles the value of the base. So this 1 becomes 1 over 2 to the s, this 2 becomes 4, 3 becomes 6, just multiplying by 2 to the s. Right. So now we can subtract this off from this. So what's that going to look like? Well, if I draw a minus sign and then parentheses, what we get is, on this side, one of these minus 1 over 2 to the s of these is just 1 minus 1 over 2 to the s of these. So that's just another way of saying you can write the left-hand side like this. Because you can all agree that 1 of these minus 1 over 2 to the s is just this value of the zeta. Okay, on this side, right here, what happens is this right here and this right here cancel, right? This and this cancel, this and this cancel, and then the a and they cancel with terms further along. So what are you left with? You're left with all the terms whose bases are not a multiple of 2, because all the multiples of 2 we already came up and we filtered it out. So we're only left with these terms whose bases are not multiples of 2. So 1 over 1 to the s, right? You can write it like that. 3 to the s, 5 to the s, 7 to the s. I'm going to write a few more terms. 9 to the s, 1 over 11 to the s, whatever. Okay, so that is one of the first steps. Well, next what we can do, we already got rid of all of the bases that are a multiple of 2. So now let's focus on the multiples of 3. See this right here? We can just go ahead and multiply this whole thing, right, by 1 over 3 to the s. Okay, so right here you can see that we just took that and then multiplied it by this, right? So this becomes 1 over 3 to the s. You multiply the base by 3 to get 9, multiply the base by 3 to get 15, 21, 27, and 33. And just like earlier, we can subtract this one, right? So from this equation right here. And what that gives us is, I'm going to go ahead and draw a subtraction sign and then 2 parentheses. Here, this 1 over 3 to the s cancels, 1 over 9 to the s cancels, 15, 21, 27, 33, all with later terms, right? So, right here, what this gives us is you can treat this guy right here as just one term, right? 1 of these guys minus 1 over 3 to the s of these guys is just 1 minus 1 over 3 to the s of these guys. So it's going to look like this. And then the part that I bracketed is going to show up like this. Zeta of s. And then on the right-hand side, all these terms we crossed out, we're not going to put those down. We just have 1 plus 1 over 5 to the s, and so on. Okay, so right here, importantly, what happened was we got rid of all the numbers, all the bases, right? That was a multiple of 2 in this step, and then a multiple of 3 in this step. So we can actually continue with this, right? Next step wouldn't be 4 to the s, right? Because all the numbers that are multiple of 4 were already filtered out, right? 1 over 2 to the s. That's what got rid of those. So the next prime number, so 1 over 5 to the s. So let's go ahead and multiply this whole thing by 1 over 5 to the s again, and we'll see what happens. Okay, so we went ahead and multiplied this guy with 1 over 5 to the s. So as a reminder in here, none of the bases are multiples of 2 or 3, because we filtered the 2's out with this step and then the remaining 3's out with this step. So now let's go ahead and filter out the remaining 5's. Okay, so right here, just like earlier, we can just subtract this bottom row out from this row right here. So doing the subtraction, and once again drawing out this long bar, just like what we did here, we can treat this as 1 and then treat this as 1, right? This right here and that right there, they're the same exact thing. So one of these, and then you have to subtract away 1 over 5 to the s of these, gives you 1 minus 1 over 5 to the s of them. So just go ahead and write it like this. 1 minus 1 over 5 to the s of these things, which is... Okay. On the right-hand side, nothing much is going to happen because all these terms that we have written out right now, there's only one of them that's a multiple of 5, right? But if you keep going, you'll find more that get erased as we do the subtraction. So all that really cancels out right now, that we can see, is this. But then if you keep writing these out, eventually you get to 1 over 25 to the s, which is still in this series. That gets canceled with this, and so on with the rest of them. So what you get is just all the bases now are no longer multiples of 2, right? Multiples of 3, right? And multiples of 5, since we filtered all of those out already so far. So what we have is... Okay, so yeah, and we can just go ahead and repeat this process with all the primes, right? We started with the first prime, 1 over 2 to the s, multiplied the last equation with that, and then subtracted it from it to get this. Then we multiplied our previous equation by 1 over 3 to the s, subtracted it off to get this. And then we multiplied this equation with 1 over 5 to the s, subtracted it off to get this. Here, you see that in that process, we actually got ourselves a bunch of factors. And notice that this number in the base right here is always going to be prime, because what we're doing is we're filtering out numbers that haven't been filtered out before. And all the numbers that have been filtered out before, notice 2, 4, 6, 8, 10, it's a multiple of 2. 3, 9, 15, 21, multiples of 3, and so on, multiples of 5, right? That means all these numbers have not been already filtered out, because this isn't a multiple of 2, 3, or 5. Right? So next number we're going to choose, they're all going to be prime, basically. So the pattern's going to continue. If you continue repeating this process, you're going to get, well, this, and then that, and then that. And then eventually you're going to get all the prime numbers in these bases. So here's what that's going to look like. Okay. So on the left-hand side, eventually, if we just keep going, we're just going to end up with this, right? We have our zeta, and we multiply by all of these guys, right? So 1 minus 1 over 2 to the s, 1 minus 1 over 3 to the s, 1 minus 1 over 5 to the s, and then just keep shoving primes into the bases, and then it will multiply on forever. But then, what will we be left with on the right-hand side, right? So I'm going to draw this equal sign. Well, if this multiplying by 7, it would have gotten rid of, kind of like how multiplying by 5, it got rid of this 1 over 5 to the s. Multiplying by 7 gets rid of this guy, 11 gets rid of this guy, 13 gets rid of that guy, 17 gets rid of that guy, and so on. So eventually, in the limit, all of these prime numbers get filtered out, and what are we left with? Well, the only thing that's going to stay consistent is this 1. So this 1 is going to be the only thing that's left on the right-hand side. So, just like that. we've kind of factored it, right? Now all we need to do is just divide both sides, right? The left-hand side, which is this row, and then the right-hand side, by all of these terms right here. So I'm going to go ahead and do that. Okay, so what I did is I went ahead and, well, as I said, divided both sides by each of these factors, right? So I actually rewrote it a little bit. This 1 over 2 to the s is just equal to 2 to the negative s, right? So that's what pops up here. And then dividing both sides, this guy right here just pops up in the denominator instead, right? So like that. So how do we generalize this, right? How do we get like a rigorous formation for this? Well, this is an infinite product, right? We've factored an infinite sum into an infinite product. So we're going to use, instead of this uppercase sigma, which we use for sums, we're going to use the uppercase pi, which we use for products. So, therefore, the zeta function of s is equal to the pi, but what numbers do we want to iterate over, right? We have 2, 3, 5, 7, just all the primes, right? So let's just put down p. That's generally how we notate that. And then what's the pattern? Well, it's just this thing, right? But you go ahead and replace this base right here with your new prime each time you multiply it. So all in all, this is what you get. 1 minus p to the negative s. Just like that. So there you go. It's factored now, right? Pretty cool.